So we can get started. So today we have a local speaker, Dr. Andrew Pace. If you don't know him yet, and he got here in September, and he's up on the 4th floor. So before coming here, he was a grad student at UC Irvine, so he got his PhD very recently, I guess in the summer, before he came here. And he gave me some notes if you want. So his research interests include understanding the distributions of dark matter in local group galaxies like dwarf toroidals, as well as low surface brightness galaxies. Some of the major projects that he did as a grad student include doing comprehensive statistical analysis of rotation curves to try to understand about cores and cusps in these kinds of galaxies, as well as what we're going to hear about today, trying to identify multiple populations of stars in these galaxies to try to understand what that implies on both the dark matter as well as the star formation histories in these galaxies. So, anyway.
Okay, thank you, Janelle. So the title of my talk is Investigations of the Inner Dark Matter Density Dwarf Galaxies. So before I get started, I should mention my collaborators. My advisor, Manoj Kapinhat, Ivo at UC Riverside, Evan Kirby at Caltech, Josh Simon at Carnegie, and then now Louis at A&M. So I'm going to talk about 3 projects that I've two are completed, one I've started here at A&M. So first I'll talk about some background. Most of the background will kind of focus on first why we think dark matter exists, and then second, what are the problems and issues that are happening with this model. Secondly, I'll talk about multiple stellar populations in Milky Way satellites, so this was a big part of my dissertation. Then I'll talk about a project that we just submitted last week, which is looking at one of these small scale problems, so the diversity and rotation curves, and seeing how we can potentially solve it with self-interacting dark matter. And then this last project is searching for velocity gradients in Milky Way satellites, which is something I started here at A&M. Okay, so first, for the observational evidence of dark matter. So if we go look at a galaxy, we look at the rotation curve. So this is observed with radio H1. We see that it rises and then it flattens off. And then if we look at what's the expected rotation curve, just from what we can see, so from the baryonic matter, so the luminous disk goes up and then it falls down, and then you have this mismatch here. And so this mismatch is basically, there has to be extra mass there, so you go, okay, maybe it's dark matter. This is seen in many, many different galaxies of rotation curves. This is basically just a pretty picture. There's at least 200 galaxies where we have nice rotation curves, where you see this evidence for dark matter. We can go to a larger scale, so this is the famous bullet cluster. So what this is 2 galaxy clusters that have collided here. So one's here, one's over here. And what you see is most of the baryonic matter in the form of gas has interacted with one another when these galaxy clusters pass through one another. So these are these red kind of shock fronts. Then if we want to learn what's the mass distribution within these galaxy clusters, shown in blue here, this is basically from weak lensing. This is kind of maybe contour plots of the distribution of matter in the galaxy. You can see that the distribution of matter is mismatched from the distribution of luminous matter. So this is kind of strong evidence for the existence of dark matter galaxy clusters. So this is more kind of direct evidence looking at individual objects. So we can go to cosmological evidence. So we can go to the cosmic microwave background of large-scale structure. So this is the temperature correlations from the CMB from the Planck satellite, and our lambda SIDM model fits the data extremely well. Basically, kind of where these peaks occur is dependent on the baryon density and how much dark matter there is. If we take this over here and we use it as an input to our n-body simulations, basically wanted to take a large portion of the universe and simulate it. This is done using dark matter only simulations, basically, initial condition, and then you get out something that looks like one of these slices in the sky. So there are 4 slices here. 2 are observations, 2 are from n-body simulations. One is from Sloan and one is from the 2-degree field survey. It's written in writing what they are, but hopefully you can't read this. Basically, I want you to identify, what's data, what's the simulation? Your kind of chi-bias says, they're pretty well, you can do this statistically, and basically says that as a whole, large cell structure prefers this lambda SIDM model. So this is great. There's evidence for dark matter from several different places. Now let's go to what are the issues with this. So if you go from your n-body model and you say, what does the dark matter distribution in an individual galaxy look like? You have that in the central regions it goes as r to the -1, and in the outer regions it goes as r to the -3. So this is basically very steeply rising in the center of it. And then you would say, okay, let's compare, go back to our radiation curve and say, do the inner regions of these galaxies match these dark matter only simulations? And so what I've done is this is NGC 3109. So this is the nice rotation curve we have here. Blue is the total fit, and the cyan line is basically an NFW halo. What you see is basically we're not fitting the inner regions, we're rising way too quickly, and then because of that we can't fit the outer regions either. And so the other two lines is one's the gas disk and one's the stellar disk. On the other hand, if we say maybe the dark matter has a chord profile, so basically goes as constant density core in the central regions, what you see is that we can fit this galaxy much better. So you can think this inner region of the rotation curve rises much more slowly for a chord profile and rises very steeply for a cusp profile. And so this is just, this is one galaxy where I said, okay, we have this mismatch between, and dark matter only predicts these cusps, and then we have these cores in galaxies. So now I want to look at this with the large sample of galaxies. So this is a plot from O et al. From the Little Things survey. Basically, they took a high resolution H1 measurements and measured the slope of the dark matter density for a large number of objects. And what they found is that most of their objects were more consistent with the chord profile. So this is written as isothermal. There's no numbers here, but this should be 0 and this should be -1. Basically, these are more consistent with the chord profile, these are more consistent with the Plessy profile, and then this is, there's data from a number of different studies here. Little things are high resolution H1, these other ones are from optical H-alpha measurements. And so what you're seeing is, on a whole, dwarf galaxies prefer cores instead of cusps. So that's one kind of small scale problem. The second small scale problem has been coined the too big to fail problem. This is basically saying, okay, let's take our luminous satellites of the Milky Way and then compare them to their counterparts in a dark matter only simulation. So basically we take our Milky Way size galaxy, you simulate it, it has a number of subhalos, and then you want to say how do these subhalo properties compare to the observed properties in natural galaxies. And what you find is that the observed galaxies, so these are 9 of the quote-unquote bright satellites of the Milky Way. These have luminosities between 10 to the 5 and 10 to the 7 solar masses, which for me that's bright. But basically these all lie in halos that span between basically 12 to 25 kilometers per second. The problem is that if you look at a dark matter only simulation, most of these satellites should be living in halos between 30 and 55 kilometers per second. So they should be in much more massive halos than what's observed. So there's two ways to kind of face this. Either there's a bunch of massive satellites in the Milky Way that are faint, they don't have stars, so why did galaxy formation fail for them? The other way to look at it is these are much less dense than they should be, and so what happened there? So there's maybe your first gut reaction is, okay, maybe the Milky Way is weird. There's just one of them. We can go to our sister galaxy, M31, you see the same thing there. You can go to the local group, look at objects that aren't bound to M31 or the Milky Way. There's a similar issue seen there, and you can even go further out into the local field where you find that dwarf galaxies are less dense than they should be. And so here's a number of citations that this happened. So the solutions to these problems basically fall into two general categories. I've tried to emphasize that these are comparing to dark matter only simulations. So obviously we don't observe dark matter, we observe galaxies. So you first say, okay, maybe because you didn't add galaxy formation into your simulations, that screwed up your measurements. So the general idea is, your subgalactic scales is modified by baryonic physics. So just comment, so this is hard to do. Many people debate about it, but it is getting better and better, and they're reproducing more realistic galaxies as kind of time goes on. The second general category is basically there's some non-standard dark matter. Our WIMP scenario is incorrect. So generally you can, so the general idea is basically say, let's move beyond this. So some general ideas, you can have warm dark matter, which basically changes the power spectrum. You can have some kind of interaction between dark matter particles. You can change the particle nature of dark matter. And then the one kind of dirty secret that many people don't talk about this is that in this scenario, you still have baryons. You still have to worry about galaxy formation. And so what I've been trying to do is to get around this debate is basically, let's go to smaller mass scales. Let's go to smaller mass galaxies. The reason why this should work is because in smaller mass galaxies, you have less stars, so there's less of a chance for this to make an effect. And if there is some non-standard dark matter, it can make a big effect here, and you can potentially observe it. So this kind of comes back to the Milky Way satellite galaxies. This is kind of my bread and butter. So this is kind of just a brief overview of these galaxies. They span a wide range of luminosities, a wide range of dynamical masses, span at the half-light radii. I'll expand on this later. And there's a large number of them now. These numbers are probably out of date now, but there's 31 in the Milky Way, there's 31 and 31, and then there's kind of 10 that are bound to the local group. And what's important about these are dispersion-supported systems. When I talked about the rotation curves, those were rotation-supported systems, so this is kind of a different type of mass measurement that we want to focus on. Okay. So how do we go about doing mass measurements in these dispersion-supported systems? So for all the galaxies I mentioned on the previous slide, basically we have measurements of line-of-sight velocities of individual stars in the galaxies. These sample size span from tens to thousands of stars. And we can make reasonable mass measurements. One of the problems, though, is that we can only make a well-constrained mass measurement at the half-light radius. This is basically that we have kind of incomplete information. We basically have three coordinates out of phase space. We have the x, y position, and we have the z coordinate. We don't have kind of proper motions. What this comes down to is basically the dark matter halo is degenerate with the scalar anisotropy. So basically, if this halo is a core or a cusp, it's completely degenerate based off kind of what kind of orbits the galaxy has. And we can't basically determine what kind of orbits they have unless we have more information. But what's been found, which is really nice, is that kind of all this degeneracy is minimized at this radius over here. So this plot is from spherical genes modeling, basically what's the implied mass as a function of radius for the galaxy Carina. Basically, for this kind of physical radius, so within like a kiloparsec, we have stellar spectroscopy for a large number of stars. I think it's about 700. And basically, so this region over here is independent. Say, like, we're extrapolating somewhere we shouldn't be. We have data for this whole region. But the degeneracies are minimized at this radius. If you want to figure out why that is, you can read this paper. But I'm just going to take it as given as basically we can measure the half-light radii well at this kind of radius here. This kind of mass estimator has turned out to be 3 times the velocity dispersion squared times the half-light radii. So, the general idea of multiple stellar populations. Sorry, let me back up. So the next part is, as kind of time has been on and we've increased, gotten larger data samples for the dwarf spheroidals, we've learned that some of the dwarf spheroidals are massive enough in terms of stellar mass that they've been able to have more cinder star formation. We've had multiple bursts of star formations, and what we found is that there seems to be a correlation between the velocity dispersion and then the metallicity of the stars in the galaxy. So this is, if you can't read this is the velocity dispersion versus radius. So this plot in the upper left here, this is the metal rich stars in the galaxy sculptor, and then these are the metal poor stars in the galaxy, in the same galaxy. What you can see here is basically the metal rich stars have a smaller velocity dispersion than the metal poor stars. What's not shown here is that the metal rich stars are much more compact than the metal rich stars. Sorry, the metal rich stars are much more compact than the metal poor stars. This is also seen in the galaxy Fornax. So there's 3 stellar populations in this galaxy, where this blue here is metal poor, the purple is kind of an intermediate population, and then this down here is the metal rich. So the general idea of this multi-component analysis is when you say each one of these stellar populations traces a different radius in the galaxy. So this one's more compact, this is intermediate, and then this one's extended. So you can think of this from each one of these stellar populations, you get a well-constrained mass for the galaxy. So you can think of this, so this is mass versus radius. For Sculptor, you have your metal-rich population that basically measures the mass at kind of closer radius, and then a metal-poor population that measures at a more extended radius. So now we're going to do something kind of simple. We're basically going to say, okay, we have 2 mass measurements of the galaxy. Let's draw a line between them and call it a slope, which is, to first order, that's what a slope is. So this is analysis basically from Walker and Penrubia that basically pointing this out, that you can use these multiple components in the galaxy to basically disentangle the mass slope. So basically you get kind of an inner well-constrained mass, an outer well-constrained mass, and then that basically tells you what the halo profile is. So these dotted lines here, this blue one is for blue one is for a cuspy profile, and then this dotted one is for a chord profile, and you can see that in both Fornax and Sculptor, this is more consistent with a chord profile than with a cuspy profile. So this is the posterior distribution of basically the mass slope here. 2 here is the r to the -1, your anisotropy profile. Then 3 here, this is rho goes to 0. This is your traditional chord profile. So both these galaxies seem to be more consistent with the chord profile than with the cuspy profile. So what I set out to do is I want to say, okay, I want to do this in more galaxies. My PhD thesis basically focused on extending this to the galaxy Ursa Minor, and I also want to break some of the assumptions that they made. So I took a lot of the statistics out of this for your benefit. But at the simplest, to disentangle the multiple stellar populations, you can think of it as a mixture model. You have a Milky Way background, and then you have 2 components of the dorsoroidal model. And each one of these components is composed of velocity, spatial, and metallicity information. So we're basically going to disentangle the populations kind of using a combination of all this information. So previously, I told you that your metal poor population is more extended and has a larger velocity dispersion. Basically, I want to kind of statistically pull this out of the galaxy, out of the sample size. What we've done is I've taken a larger sample from DEMO, so we have about 1,200 stellar spectra. I think there's about 1,000 that are repeats, and then there's some that are obviously non-CMD members. And so the first thing that we want to do is we want to disentangle what's in the Milky Way and then what's in the dorsoroidal here. So this color bar basically shows the probability of being a member of the dorsoroidal. So So Ursa Minor versus 0, this is a Milky Way background star in our model. And basically you have kind of a well-constrained locus in velocity and metallicity space. And similarly, this is kind of centered on the galaxy. Our observing pattern has a kind of a weird structure to it. So that's kind of the first part. We basically can well separate out background and Milky Way stars. And now we want to say, within the Ursa Minor stars, are there two stellar populations? And so since I went through all this introduction, you can probably that there are. So on the left-hand panel, the color bar basically shows stars that are more likely to be in the metal core population. So this has, you can kind of see that the spread in velocity is much larger than the spread on the right-hand panel. And then they're also much more metal core compared to this population. So this is, lower velocity dispersion, more metal rich. And we also see similarly that this, so this is still the metal core population, but this is more spatially extended than the metal rich population. And then this metal rich population is much more asymmetric than the metal core population. Okay, so now we want to kind of compare how do the kinematics change with radius. So as I said before, you have this metal core population that is more kinetically hot. So it basically follows radius and is constant. Then the metal rich population is basically constant with radius. So the top panel is velocity dispersion, and this bottom panel is average line of sight velocity. And it varies versus elliptical radius here. So this is kind of the kinematic side. If we look at it in metallicity, you can see that you have a metal rich population and a metal core population. And this is basically the spread of the populations. What I want you to get out of this is that they're distinct in basically kinematics, metallicity, and in spatial position. One thing that's disconcerting is they're quite close in metallicity. But I'm kind of confident in the method basically because I can put in mock data and get out what I put in. Okay, so now how do these populations compare to NFW halos? So this is kind of the big summary plot. So this is circular velocity versus half-light radius. So first we want to look at the Ursa Minor. So Ursa Minor here is in magenta. So there's two components. And what you want to do here is you want to say, can we fit both of these components in the same NFW halo? So each one of these bands is kind of the range of NFWs that have a Vmax of 10, 20, 30, 40 kilometers per second. Basically, you can think of this spread as the different spatial scales that the profile can have. So the first thing you can kind of look is these are not consistent with the single NFW, but at the same time, it's very hard to fit a line between the two of them in 0. So let's turn away from Ursa Minor and let's look at Fornax. So as from the Walker et al. Analysis, I showed that basically Fornax is consistent with the core. So these blue points are from Fornax, and you can kind of see that this is kind of a slow rise that's expected from a core profile. Whereas Ursa Minor seems to, rise slow, and then this one is way too high. So there's two things to get out of this. One is that two of the systems with multiple stellar populations, Fornax and Sculptor, seem to be inconsistent with NFW halos. The second is Ursa Minor is just weird. There seems to be some kind of problem with using this method and the dynamical equilibrium of the system. Okay. Any questions?
So you can't, can you extend this to other dwarf toroidals, or is the problem the number of stars?
So This kind of, okay, so I'll kind of go here. There are multiple problems with my Ursa Minor analysis. One of them is basically how we chose for the masks on the sky. This basically has introduced some kind of spatial bias to the data that I'm still kind of trying to back out. Basically, if I put in mock data, I observed it like we do. The populations I observe is more elliptical than it should be, just because we put more masks along the major axis. So basically, these two populations should shift around a little bit. Basically, there's bias that I haven't uncovered with them, which is one reason why this is so important. Okay. So just to summarize, there are two hemodynamical populations that have high significance. This is in terms of base factor, and similarly, I can connect mock data with similarly high significance. The mass slope I infer is unphysically large, and there seems to be the populations I infer. First of all, they're close in metallicity. One is very disky compared to the other one that's very spherical. And then there's this other thing that I can talk about. Ursa Minor may contain cold substructure, which if you're curious about, ask me later. Okay, so that's the multi-population summary. So now I'm going to move on to self-interacting dark matter. And before I do that, I have to introduce another problem, because this is the problem that we set out to solve. So this is basically what's been called the diversity in observed rotation curve problem. So in the upper left panel, we have all these plots are the maximum circular velocity versus the circular velocity at 2 kiloparsecs. If we look at dark matter only simulations, you can see that there's a very tight correlation between basically the maximum circular velocity and then the velocity at 2 kiloparsecs. This is the mass halo concentration relationship. If now we go to hydrodynamic simulations, so this is the upper right-hand panel, similarly we see a very tight correlation between the maximum circular velocity and the circular velocity at an inner radius. Now what they did is they basically said, okay, let's take a compile of all the different rotation curves and say, what's the maximum circular velocity compared to what's the circular velocity at 2 kpc? And what you can see here is that there's an enormous amount of spread. Much larger than seen in the dark matter only simulations, much larger than seen in the hydrodynamic simulations. And so the question is, why is there all this spread in these galaxies? So all the galaxies at 100 kilometers per second, these should all reside in the same kind of dark matter only same mass dark matter only. Sorry. The same mass halo. But this halo seems to have very diverse properties within its inner regions. So the question is, why is this? And so we set about to address this in this self-interacting paradigm. So why did we choose self-interacting dark matter? One of the big benefits of it is that in terms of large-scale structure, it doesn't change the picture. So on the left here, I have a dark matter-only simulation, and on the right here, I have a self-interacting dark matter simulation. And what you can see is that in terms of large-scale structure, these are very similar. And at least by eye, I can't tell any difference. If we now zoom into a Milky Way-sized halo, you can see that this galaxy, so this is the dark matter density, rises very steeply in the center. And if you compare it to the self-interacting dark matter halo, you can see that it forms a core in the central region. So you can think of this as the self-interacting dark matter model basically preserves the success of large-scale structure. We're only making modifications on small scales. And for reference, this is a cross-section of 1 centimeter squared per gram, which is about the interaction which is about the cross-section for a neutron-proton interaction. So how do we model the SIDM halo profile? So what's nice about SIDM is that it adds in self-scattering to the dark matter. So now the dark matter can exchange energy, it can thermalize, and it makes basically an isothermal velocity profile in the inner regions. So for the inner regions of the galaxy, it's going to be isothermal. And then in the outer regions, it's going to follow the NFW profile, this success story of cold dark matter. And then there's some radial scale that determines where we go from our isothermal SIDM profile into the dark matter only profile. And so this radius is set by basically, within this radius, there should be one scattering per dynamical time. Basically, there's been enough scatterings to thermalize the dark matter halo in that region. And so this is basically set by this relation here. This has been fit to self-interacting dark matter simulations. So first, Ursa, and then in Albert et al. So just an example of what it can do, this is the Galaxy IC2574. This is from the Thing survey. The solid line is the dark matter halo. The dashed line is the gas disk, and then this dotted line is the stellar disk. And it gives a reasonable fit. I should say that basically if you put any general chord halo, you'll get a good fit here. This is not some, SIDM can do this. If you can chord the halo profile, you can fit the rotation curve. But what's nice about this model is that we can tie together the self-scattering interaction rate to the halo properties. So the next part is basically including the baryonic effect on the SIDM halo. As I said before, even in your non-standard dark matter models, you are going to get an effect from galaxy formation. And so the general cold dark matter only case, you have there's an effect called adiabatic contraction. This is basically if you have a galaxy in your dark matter halo, the potential well is deeper in the center, so now the dark matter particles feel like we put a potential, and so that will steepen the center region. This is a similar effect, only now they're self-scattering, so the dark center can exchange energy. So if you go to the density profile of an isothermal halo, it scales as the exponential of the potential, and the potential here is the total potential. So it'll feel kind of a larger effect from the baryonic potential than the dark matter only case does. And so what we did is that we solved this in axisymmetry, basically doing a Legendre expansion to take into account the exponential disk. And on the left-hand side, I show the effect of the baryonic effect on the SIDM halo. So in magenta here, this is the gas disk, and this is the stellar disk. And these asterisks are basically, that's the SIDM only situation. This solid line here, that's the SIDM plus baryonic situation, where the gas disk, the stellar disk has greatly steepened the density profile of the halo. And just for reference here, this dotted line is the NFW profile. So what we set out to do is basically say, we want to try to explain this diversity. And so there are two parts to explain it. So the first part is basically the spread in assembly history. So this is the mass concentration relationship. This is basically, so these, this is the SIDM only in cold dark matter case, where you have a halo with a B mass of 70. And basically this spread here tells you what's the spread in assembly history. And so this was, if you recall back to the Owen et al. Plots, this was the top left-hand panel. And so the effect that we wanted to point out is basically is if you have self-interacting dark matter, depending on what galaxy you put into the halo will feel a response that changes based off the surface density. So this is a galaxy of about 10 to 11 in halo mass, 10 to the 10 stellar disk, and basically these are different different values for the stellar disk. And basically what you can see is that depending on how, what the surface density of the stellar disk is this will increase the self-interacting dark matter circular velocity profile. So you can think of this, there's some spread encoded on what galaxies live inside what halos, and this basically will introduce spread in addition to the spread within halos. So to quantify a little bit, what we did is we went to the Ohm et al. Plot. We looked at a given mass range. So we looked at 80 kilometers per second and said, what's the minimum, what's the maximum, what's one in between. And so this is how we got these three galaxies here. UGC 5721, this is a galaxy where the rotation curve rises very steeply. And over here, this one kind of rises at an intermediate rate, and this one rises even slower. It's kind of hard to tell because this rotation curve is much more extended than the other two. But this is basically an example where your SIDM halo is greatly affected because of the large stellar disk within the galaxy, whereas these two have less of an effect just because there's less baryons within the galaxy. This is basically saying we can explain this spread basically given different dark matter halos and given the galaxies that are within them. We also looked at some larger mass galaxies. So this is NGC 6503, which I showed earlier. And then this is UGC 128. So what's interesting is these both roughly have the same circular velocity, but one has a very high mass, high stellar mass galaxy inside of it, and this is much lower. And so you can see that there's a large effect from the SIDM halo here, whereas it's much smaller here. And it has an even larger effect in a larger galaxy. So if you want more details, we put this on the archive last week, so you go ahead and read that. And the one thing I want to emphasize here is we basically said, can we solve this problem here? Yes, but I don't think, so we've shown that we could solve it, but not that it does solve it. Basically, we only looked at kind of 20 to 30 galaxies and basically said, okay, we can fit all these galaxies, but as a prior, we assumed the concentration mass relationship. If we want to show that it solves that, we should infer that relationship from the data. So just to summarize, the SIDM model can create cores in dark matter halos. It lowers the dark matter densities, and it has the same success in large-scale structure. And then hopefully I've shown that it can explain the diversity and rotation curves basically from two effects. Are there any questions for SIDM? I'm about to make another jump.
So did you consider other, in this, I haven't read your paper yet, I'm sorry.
That's fine.
Did you consider other models, dark matter models?
No, this is basically saying, can SIDM do it?
Okay.
There's some theoretical bias there.
That's great. I'll go read your.
There's a lot more rotation curves in the appendix of the paper. Okay, so now I'm going to jump gears a little bit and go back to the Milky Way satellites. Basically, the Milky Way satellites are within the virial radius of the Milky Way halo, and they should feel a tidal effect from the Milky Way halo. The question is, how large is that, and what does it have an observational effect? So in a recent study of spectra of Leo 5, Michelle Collins basically found that there is a very large velocity gradient within the stellar spectrum. So the average velocity of the galaxy is about 170, and then there's this large gradient that's observed along this axis. So the other thing is that there's some evidence based off the photometric properties of the galaxy that it's having an interaction with the Milky Way. The problem, though, is that you're drawing a gradient off of 8 stars. So what we wanted to do is say, how significant is this? Basically, how likely are you to get this in a null model? So we went ahead and computed that, and we found that, it's the velocity gradient model is favored, but not significantly. And then we noticed that no one else had done this for the Dwarf toroidals in general. So we set out to basically say, let's search for velocity gradients in all the Milky Way satellites that have spectroscopy. And then there's 2 classes of Dwarf toroidal galaxies. There's the classical bright satellites. These are mostly all pre-Sloan, and they have very large sample sizes. Then you have the ultrafaints that have small sample sizes. This is partly because they're discovered later, partly because it's hard to get spectra for them. So we went ahead and did this for all the galaxies that we could, and we found velocity gradients in 3 galaxies. One of these is Leo 5. We found a velocity gradient that basically agreed with the Collins analysis. And then we found a velocity gradient in CV2 and Coma-Bernices. So what these plots show is this gold line is the average line of sight velocity of the galaxy, and then the spread here is basically the spread that's expected from just the velocity dispersion. And then this magenta line is the gradient that was found in the galaxy, and the spread based off the velocity dispersion in the gradient. CV2 was our most significant detection. It's entirely dependent on this outermost star here. If you take away that star, the velocity gradient goes away. Coma-Bernices is a better case where if you kind of look along the gradient, you can say, up here there's more stars at larger velocity, and over here there's less stars at smaller velocity. So these stars, these galaxies, the velocity model was favored, but in the other galaxies there are lots of kind of quote-unquote non-zero detections, but it's still not, the null model, just kind of a velocity dispersion is not ruled out.
When these people calculated their velocity dispersion, did they, in these 3 cases, did they account for the gradient? Because it would, at least in Coma-Bernices, we would have that, right?
Yeah, so the other thing to note is that in the velocity gradient model, all the velocity dispersions are lower than in the model without the gradient. So you can kind of think of this as the spread you see. It's either discerned by velocity dispersion or by a velocity gradient. And so you can think of it, there's some spatial correlation that goes into the velocity gradient model also. So now the next part we wanted to do is we wanted to say, how do the velocity gradients that we found compare to other indicators of tidal disruption? So there are 3 that we looked at. The first is the distance to the Milky Way. Basically you say, galaxies that are close to the Milky Way feel a strong tidal force, so they should potentially have a larger velocity gradient. The next is the Jacobi radius. This is basically the radius, the maximum radius where you have where the Dwarf toroidal dominates compared to the Milky Way potential. And then the last one is stellar ellipticity. Basically, is if you see an elliptical system, it could have been stretched by the Milky Way potential. So there are 3 subsystems. Basically, the magenta here are the bright systems, and then the gold and cyan are the ultrafaints. The cyan ones are the ones with very small spectroscopic samples. But basically, it looks like a lot of the ultrafaints have some sign of a velocity gradient. You know, these guys all have one close to the Milky Way halo, but then, you know, all these systems over here have a larger velocity gradient also. So what's going on? You know, is this tidal disruption? Or is it some effect of the sample size? So if you basically compare this to the luminosity of the system, the size of the system, and sample size, you basically see that, you know, you can kind of see the correlation here, where the fainter systems have larger velocity gradients, the smaller systems have larger velocity gradients, And then the systems where you don't sample it very well have some indicator of velocity gradients. So this seems to me, at least as a whole, that maybe it's not tidal disruption, maybe it's just an observational effect. So one of the things that we're quantifying right now is if there is a velocity gradient, how many more stars you need to observe to actually show it conclusively. Any questions about velocity gradients? Tidal disruption? Okay. So these are my brief conclusions from each project. I will leave them up there for you guys to read, and then I will take questions.
Questions?
So if you take one of these classical dwarfs that has a velocity gradient and you subsample it, or you make it look in some way, make those data look in some way, like you think?
So
I mean,
what-
that's not the obvious, I guess.
So one of the things I've done is I've taken CB1, which is, it was discovered in Sloan, but it's bright enough to be a kind of a classical system. And basically I said, let's observe half the sample and a quarter of the sample, and then put in a velocity gradient and see how often I can recover it. And if there's a velocity gradient of 20 kilometers per second, I can recover it at a significant amount where I would say there's a velocity gradient in that system. But the thing with, the one thing I didn't mention is, if you looked at Leo 5 and Coma Berenices, they only go about 100 parsecs along the gradient axis, where if you look at the data I have for CB1, it goes to about 600 parsecs on either side. So basically you kind of need a larger sample size and you need a more extended sample size, which is hard to do for the local points.
So for your multiple population stuff, so you're getting masses using the low-pass filter.
Yes.
I mean, is there a need to go beyond that, like
So-
distribution function stuff? Or?
One of the things that I want to do is I want to, basically the separation that I've done basically assumes that there's a single velocity dispersion for each model. I've also done like a functional form for it. You can say, you could do kind of a joint spherical genius model where you say they both live in the same dark matter halo, but they have different stellar distributions and different anisotropy distributions. And so that's one thing that I tend to do, and that basically that can infer the dark matter halo without kind of the slope estimators.
Anything else? I guess since there's some time left, you mentioned the cold structure in Ursa. What?
Basically is if you look at, okay, so the background of it is if you look at the photometric structure of Ursa Minor, there's a second density peak, and besides the one that's in the center. And people have argued about the significance for this while. So the first study I mentioned, Klein et al., basically they looked at stellar spectrum and they said, at this secondary photometric peak, the velocity dispersion is much colder than in the main halo. They quoted basically 0 kilometers per second for the stars within that region. And one of the reasons why we got more spectra for this is basically that when I did this analysis with slightly larger samples, I said, oh, it's not 0, it's about 5 kilometers per second compared to the total one, which is 10. So basically, there might be some kind of localized substructure in the galaxy, which is being confused with kind of global structure. The idea of what this is it could be like a dissolved well-beer cluster, and that can tell you something about the dark matter halo also.
Any other questions?
Do you want me to ask a question?
Yes, please.
So Chris, I love this stuff. I'm always fascinated by self-interacting dark matter. So I guess again, my question would be, how unique the prediction from the self-interacting dark matter be compared to some of the other theories that are out there, or other issues that may
Like,
some of the problems with dark matter models?
what kind of prediction do you want?
Something observable. But yeah, right. That's a good question. Right?
So one of the ways, if you go to the lower mass galaxies, these should all have cores in them. And there shouldn't have been enough, there isn't enough kind of stellar matter to kind of the lambda CM solution is basically feedback, where you have a supernova go off and it kind of drags some of the dark matter with it and it creates a core. So the idea is you have to go in a small enough galaxy where there aren't enough stars for that to be a big effect. But if it's self-interacting dark matter, the dark matter should thermalize in all galaxies. So that's kind of one of the reasons why I'm going down to lower mass scales. So one idea is you want to go to try to observe rotation curves in kind of field dwarfs at very low masses. So I guess my response to that is basically you want to observe a core in a very low mass galaxy, a low stellar mass galaxy.
Yeah, that makes sense. I was just thinking, of course, if you have a situation where there aren't many supernovae going off, or something, there aren't many stars in the core, so the baryonic solution for feedback baryonic would work. Then you also just don't have many stars to begin with.
Yes, that's the other problem with it. And also in a lot of the galaxies with gas that get down to this mass range, you don't have, you don't see rotation within the gas itself. So you
Okay,
get,
so it's just a hard problem.